In this lecture, we will discuss about the Kutta condition, Kelvin circulation theorem, and we will start discussing about thin airfoil theory. So, in the previous lecture, we had looked at the Kutta-Joukowski theorem, and you may remember that we obtained lift per unit span, and that was found to be equal to the product of gamma, the circulation around the circular cylinder, and the product of rho u infinity based on the free stream values. Now, the concept of Kutta-Joukowski theorem extends to arbitrary geometries. So, it is not mandatory that we just look at a cylindrical geometry and have a feeling that this theorem would only apply to such a geometry. It applies in general to arbitrary two dimensional geometry. So, let us say now if we look at flow past an airfoil, then if the airfoil is generating lift, in that case the same expression would work for the airfoil, and that basically means that if we take a curve, a closed curve around the airfoil enveloping it, and we compute the circulation around it, we will come out with a non-zero value of the circulation. So, there are different ways of looking at how the lift is being generated. If you go to the basics, it is ultimately a pressure distribution which is acting all around the airfoil. Since it is a potential flow, we do not talk about the shear stress distribution, it is only the pressure distribution and an imbalance between the upper and lower surface pressures that is creating the net lift, which basically means that there is on an average higher pressure on the lower side and lower pressure on the upper side that is causing the lift force. And for potential flow, we do not draw the drag force at all. Another way of looking at it is that there is a net change in the flow direction as it moves past the airfoil, and thereby there is a change in momentum which is responsible for the lift force. Another way of looking at it is that there is a net circulation around the airfoil, and based on the Kutta-Joukowski's theorem, we can quantify the lift per unit span based on the circulation. The convenience with circulation is that we do not really need to look at the pressure distribution about the entire airfoil, but we just have a single number which can tell us that how much lift the body is generating. So, lift generation from the perspective of a net value of gamma is a very convenient concept. Now, we can conceive gamma as a single vortex placed at some convenient point on the airfoil, or in the form of a discrete set of vortices which are distributed along the surface of the airfoil in the form of a vortex sheet. So, this vortex sheet is wrapped around the airfoil with a certain distribution of vorticity. But when the airfoil is very thin, you can approximate it to the camber line and distribute the vorticity along the camber line and say that it is going to give us a fairly approximate picture of the actual surface geometry. There could be another level of simplification, which we will discuss further as we move into the thin airfoil theory, where instead of having the vortex sheet along the camber line, we propose a thought that whether we can have it along the chord, but still make the camber line as a streamline of the flow. So, we will discuss that concept in due course. Now, as you look at the vortex sheet, the total gamma value could be shown as an integrated effect of the gamma distribution along the length of the vortex sheet, where S is a particular location on the vortex sheet itself. And once you get the gamma from the Kutta-Joukowski's theorem, of course, you get the value of lift per unit span. And if you look at any particular region of the vortex sheet and you notice the tangential component of velocity above and below it, then you would see a jump in the tangential components, and the local strength of the vortex sheet will be given by the difference of the tangential components of velocities. So, the tangential components are indicated by u1 and u2 above and below the vortex sheet. So, there is a jump in tangential velocity across the vortex sheet. So, you could also consider it to be a layer which brings in shear in the flow. Let us look at Kutta condition and the concept behind it. So, we were looking at an airfoil which is generating a certain amount of lift. It is at a given angle of attack, and at that angle of attack with a given airfoil, we will always end up getting an unique value of the circulation. How does that happen, and when does that happen? It happens when the flow, when it moves past the airfoil, smoothly leaves from the trailing edge of the airfoil. Now, what do we really mean by that? It depends on the trailing edge geometry. You could be having a finite angle, let us say theta, at the trailing edge. So, this is your trailing edge, and potential flow approaching the trailing edge from the upper and lower surfaces of the airfoil. There is no guarantee that those velocities would be equal in magnitude. So, in general they are different in magnitude. They are obviously different in direction because they are approaching the point, the trailing edge point, from two different directions, and there is a likelihood that they would cross over at this point, but then if they do so, you will have a non-unique value of velocity at the trailing edge, which is not possible. You will always need to have a unique velocity at a given point of the flow field. So, in that case, what is that nature does in order to take care that you have a unique value of velocity at the trailing edge where the two streams are meeting? What nature does is that it sets the two velocities to 0 at the trailing edge, and therefore, it becomes a stagnation point. Once that happens, the flow would leave smoothly, ultimately in the form of two streams mixing smoothly with each other and moving downstream, where there is this stagnation point at the trailing edge, and there would be a stagnation streamline further down. That is how the flow would behave. What if instead of having a finite value of theta, the theta was approaching to 0? That is when you have a cusped airfoil. This is where the theta is approaching to 0, or the theta of the upper and lower surfaces are approaching each other. That means the inclinations of the two surfaces are approaching each other. In that case, the velocity directions are identical, but then again, if they have different magnitudes, you will have a pressure jump across these two streams. If you apply the principle of P plus half rho u square remaining constant, because the u's are different and therefore, the P1 and P2 would be unequal. Now, the kind of flows that we are handling, incompressible flows, cannot support such pressure jumps. You will see later that high speed flows can, but in this case it is not allowed. So, how can that be resolved? It can be resolved if and only if these velocity vectors are identical to each other, not only directionally, but also in terms of magnitudes, which basically means you have two streams moving parallel to each other with the same magnitude of velocity. So, finally, if we were to look at the gamma at the trailing edge, where we already found that gamma is defined as the difference between the tangential components of velocity at a given point. From that concept, it will be v1 minus v2 vectorially. And in the first case, we found that it is identically 0 because it is a stagnation point, while in the second case they are equal to each other. So, in either case you get gamma trailing edge equal to 0. So, what does it finally say? It says that at the trailing edge of the lifting surface, the strength of the vortex sheet has to go to 0, only then the flow would leave the trailing edge of the lifting surface smoothly. So, this is Kutta condition. So, a smoothly leaving flow will always end up satisfying this condition. It all began when the flow first reached the airfoil. So, there was an uniform flow which was approaching the airfoil, and when it reached the airfoil, then the airfoil started generating lift. But before it did reach the airfoil, if you took a closed curve around the airfoil and you found that the velocity was 0 everywhere, the gamma would come out to be 0, and of course, hence the lift would be 0. Let us say it is at t equal to 0, the time is t equal to 0, and then at time t greater than 0, the flow reached the airfoil, and then the airfoil started generating lift, the pressure distribution came up on the airfoil, and instead of distributing the vorticity all over, let us say that we mark a single vortex associated with a circulation gamma 2, y 2 we will see very soon, because we want to mark gamma 1 elsewhere, which we call as the bound vortex. So, instead of a distributed system of vortices along a vortex sheet, for example, we have it lumped at one point, which we call as the bound vortex. So, the u infinity reached the airfoil, the pressure distribution developed, and as a consequence, a circulation developed around the airfoil. And if you were to follow the same set of fluid elements which you had identified at t equal to 0, you would find that they are now going to contain a sheet of vorticity which has been shed into the wake, which we call as the starting vortex. So, the vorticity has been shed from the trailing edge of the airfoil as the flow established itself, and it moved into the wave. How much circulation was contained in this starting vortex? Let us call it gamma 1, and of course, both gamma 2 and gamma 1 are changing with time. As time elapses, we would find that the values keep changing, but the total circulation content of the same set of fluid particles that we ended up tracking gets expressed through the relation that the material derivative of circulation is equal to 0. That means, the total circulation that these fluid elements contain would not change with time as you follow them dynamically. That is why we bring in the substantial derivative into the picture, and this is precisely the Kelvin's circulation theorem. And in irrotational flow fields, there is no mechanism by means of which you could change this value of gamma with time if you are tracking the same set of fluid particles. As you track the total gamma that these fluid particles carry with them at all times greater than 0, the gamma remains conserved, which basically means that if you sum up gamma 2 with gamma 1, the sum will always remain 0, which basically means that gamma 1 is equal to minus gamma 2, which means the starting vortex which has been shed into the wake will have a strength which is exactly the same as that of the bound vortex in terms of magnitude, but opposite in direction. So, you see that this is marked counterclockwise, while this is marked clockwise. That is the sense of the rotation. As time becomes large enough, then what happens is the gamma 2 t tends to a constant value. So, that is the gamma airfoil at steady state. And then we find that no more vorticity would be shed into the wake, and the starting vortex would have advected far downstream, and then you will be left with only the bound vortex on the airfoil, or in a distributed sense in the form of a vortex sheet. So, with these concepts in mind, let us move into thin airfoil theory. We have been developing the tools which are important for discussing this theory, and we are now rightly placed to look at the details of the theory. So, what do we have here? We have just drawn a camber line representing the lifting surface, the airfoil. We are having S as the coordinate of any point on the airfoil. This is the leading edge, the trailing edge, the chord length, and then as we were discussing the vortex sheet, we said that we would like to deploy the vortex sheet along the camber line, but then if the camber is not very significant, and of course, that the airfoil is very, very thin, in the given situation, if you look at the airfoil from a distance, you will have a feeling that the vortex distribution that you have in the form of a sheet can instead of being located along the camber line, be as well located along the chord line. There are some advantages associated with this, of course, from a mathematical point of view, but this would not be very erroneous if we have the given circumstances that the camber is small, the airfoil is thin, and we are looking at it from a distance. But we will continue to say that the camber line is a streamline of the flow. And then what should we ensure? That there should not be any kind of a cross flow allowed across the camber line. Only then can the flow remain tangential to the camber line, and therefore, it becomes a streamline of the flow. Of course, we need to find out what this distribution of gamma should be, and now that we have redefined gamma as gamma x rather than gamma s if it was deployed along the camber line, we would actually have to find out gamma s, but now we have reduced the problem to finding gamma x, which is along the chord line. So, we need to find gamma x, so that we can make the camber line a streamline of the flow. Additionally, we have to make sure that the strength of the vortex sheet goes to 0, gamma c should go to 0 at the trailing edge, because that is what Kutta condition says. So, let us say if we identify the velocity component normal to the camber line, then that velocity component in a net sense should be 0. So, one part of it will be coming from what is induced by the vortex sheet, the other part of it will be coming from the free stream. We should not forget the free stream, which is coming from this side. So, it is a combined effect of the u infinity coming in at alpha and the w component of velocity, because we are marking this as z, which is acting by virtue of the vortex sheet. Now, strictly speaking, this should be normal to the camber line, and we would therefore mark it as w suffix n s. So, it is not exactly the z component, but the one which is normal to the surface. And remember that at the same location x, if it is on the chord line, it will boil down to finding precisely w at x, because that will be exactly aligned along the z direction. Once we find out the gamma distribution, we integrate it and then we will get gamma, and from gamma we will get lift. This is the whole idea. So, let us look at the geometric details a little more before we write down the relations. So, we need to have more clarity on the geometric issue. We identify a particular point on the airfoil, let us call it P. Let us draw the tangent at that point P and the normal, and let us look at the velocity vector. So, the velocity vector is coming in like this at an angle of attack alpha. So, this is alpha, and you can draw another line here which is tangential to the tangent that is drawn at the point P. So, you can see that this angle turns out to be tan inverse minus dz dx. Of course, dz dx happens to be the slope of the camber line. Now, if you were to look at the normal component of the free stream velocity, then you have to account for this entire angle, and you will have to take sine of that angle. So, u infinity n, that means normal component of u infinity at that point P would be given by u infinity sine of this entire angle, which means sine of alpha plus tan inverse minus dz dx. So, we have found out the normal component of u infinity. Now, this normal component of u infinity summed up with the normal component of the velocity which is induced by the vorticity distribution should go to 0 uniquely at each and every point on the camber line. Only then the camber line becomes a streamline of the flow. because they do not allow any normal component of velocity in a net sense in that case. Now, if alpha is small and the camber is also small, then we can approximate this expression as u infinity times alpha minus dz dx. With this simplification, and additionally, if we assume that the normal component of the induced velocity due to the vorticity distribution is approximately equal to w x, that means it is aligned exactly along z rather than along the normal to the point P, then we have two simplifications put together. That means, the resulting expression in that case will be looking like this. Now, let us see how we can quantify this in terms of the gamma distribution along the chord. So, for that we draw a simple sketch to explain how we can do that. So, you have the vorticity distribution along the chord, this is your entire chord length, and then you identify a location somewhere in between on the chord which has a length d xi. Xi is a dummy parameter, and this small elemental length is at a distance xi from the leading edge. So, this small element is inducing an elemental vorticity which can induce an elemental v theta component at a field point. This field point has coordinates x z, which can also be written in terms of r theta. Now, we know from the concept of point vortex that we can calculate v theta for a point vortex using an equation like this. Now, here we have a very small vorticity within that d xi length, which can induce a very small extent of v theta that will be given by this value. So, the strength of gamma over that element times the length of the element, that gives the vorticity, and that replaces the gamma. And remember that v theta is positive when it is counterclockwise, while gamma is considered to be positive when it is clockwise. Therefore, a clockwise gamma will end up producing a clockwise v theta. Keep this in mind. So, that comes from the negative sign in this expression. Now, the velocity d w at a point x induced by this elemental vorticity will be given by an expression like this. So, the idea is that this elemental vorticity, how much w will it induce at some other location x, which is on the chord line itself. So, at that location, this is the d w that it induces. So, if we sum up these d w's by taking in account all the elemental vorticity that we have spread along from leading edge to the trailing edge, we have an expression like this, an expression of w x given like this. So, once we have that, we have the final equation for thin airfoil theory, which is and this is precisely the equation which ensures that the Campbell line is a streamline of the flow. So, in this lecture we discussed further relevance of the vortex sheet to model flow past a thin airfoil. We then discussed about the significance of Kutta condition to fix a unique value of circulation around an airfoil, which is achieved when the flow leaves the trailing edge of the airfoil smoothly. Then we moved on to Kelvin circulation theorem, which was discussed in the context of starting vortex and growth of bound vortex to the steady state value. And then finally, we looked at the background of thin airfoil theory and we ended up obtaining the final equation for thin airfoil theory. Thank you.